Hey everyone, my name is Mannan Venkatesan. I work in network architecture in Comcast, primarily focusing on the backbone and the regional IP networks. Um, I want to thank the committee to give me this opportunity to share our backbone evolution we had over the last few years. We wanted to go over some of the challenges we faced, how we addressed them, and some of the learnings we had in our backbone deployments. So thank you for the opportunity. Um, so before I start going into the details, I wanted to share this slide. Most of you would know this already. Just wanted to give you an overview of backbone core networks, their capabilities, and their functions. Typically, the backbone networks are the big mega routers supporting hundreds of thousands of ports, carrying multi-terabits of traffic, critical traffic, interconnecting all the routers and sites, regional networks, external peers, external providers, provide them connectivity between those networks it connects to. The routers we use in backbones, typically they are scale out or scale up hardware. Scale out meaning we expand the router across multiple racks. Multi-chassis is an example. A few vendors came out with a multi-chassis design. Multi-chassis is one of the examples for scale out option. And scale up means we would upgrade the hardware at regular intervals once in a few years, or we would replace the whole box with a new denser box. That's a scale up options. These are all critical backbone core routers supporting millions of customers. They support all the traffic flows, all the services that we provide to our customers. Though I am showing you a single router design in this slide, I have seen other designs where folks would use two routers in a backbone location, connect them back to back, and provide the port density they would need to support. And I also have seen 3 or more routers connected in a ring fashion or a star topology fashion to support the density they would need to support their growth. So moving on to the next slide. I wanted to start with some of the challenges we were facing with the core router platforms. I have listed a few of these challenges here in this slide, but I would go through them in detail in the following slides. And they're starting from the port capacity we need to deploy to support the traffic growth. Some of the bandwidth and features of ASIC chipsets we have to deploy, cost of the software and the hardware, and blast radius, that's a failure zone, and maintenance window followed by the environmental constraints. We have to deploy them in both Comcast footprint or our internal footprint, as well as our co-location facilities. So the first challenge I would like to start here is the port growth we need to support. We all know, the internet traffic exploded last decade. The red graph, the red line shows the internet traffic volume we have to support in our backbone, in your backbone too. It's exploded in the last 10 years or so. So the ports we would need to support the traffic is also proportional to the traffic volume. So we have to make sure we stay on top of the port capacity we support on this core routers. That's the blue line you see. If I go back to my start of my career with Comcast, we were using 1 gig ports those days. Then we moved on to the 10 gig ports. Then we were doing multi 10 gig links. Then we moved on to 100 gig, and we survived with the multi 100 gig ports for a few years. Now we are looking into 400 gig links. So that's the step function you would see with the blue line. It's driven by the port capacity or the port speed and the platform capacity to support those ports. So depending on which which year to look at. If you look at the end of your platform lifecycle, you're always running behind with the demand. So you always at the beginning of the platform lifecycle, we have enough ports to support to meet our demands, but we have to stay on top. But when you come closer to the end of the lifecycle, we got to make sure we have enough ports on the box, or we bring in a new platform or new hardware to support the demand. So that's always a challenge that we have been facing. And the next challenge is the failure zone, or the blast radius, we will say. If we lose one router in a core location, we impact millions of customers. If it is a hard failure, then the packet on the wire is lost. Then during the convergence, we may impact some flows. But if there's a partial failure, if the box is starting to misbehave and start blackholing traffic, we will impact millions of customers with those failures. So it creates a snowball effect, impacting the regional networks, core links, as well as our inter-provider links, our peers, all the traffic between this network we connect to. So if we lose one of the router in our core location, at the same time, if you lose another failure, if you have another failure in a connected network, this could lead into a disaster situation. For example, if you lose site 1, all our providers would start sending traffic through site 2, 3, and 4. But during the same time, if we had another failure in their network or in our network, we would have a much better impact to our customers. So one of the goals here is to reduce this blast radius. The next one is the economics and features. We have seen over the years, the more bandwidth we support in a box, the features supported is kind of taking an impact. The per port cost, it's higher to support complex features compared to basic IP routing features. And then it's really difficult to mix different port profile, different profiles with different requirements in a single chassis. So as I show in this graph, if you have 3 or 4 different profiles, we end up supporting ports that would support all features in the box. So we would end up probably paying more money for the box than if you were to support the basic IP routing features. Though the backbone is a pure PE function, but this applies to our edge role also. So if you have a big box supporting your PE roles, you will end up seeing the same problem there too. The other thing we have seen, the per port cost of a multi-chassis router is a lot more expensive compared to the fixed or modular chassis routers. So we got to account for this economics as well as the features as we start deploying these big boxes in our network. Then the operational challenges. We could come up with a cool technology, or we could come up with this brilliant architecture, but they are not good enough to deploy unless we make them supportable in our network or any network. So we got to make sure we put our operational hat on. We got to make sure whatever we are rolling out in a network, they are supported by our operations team. Over the years, the number of hours we get for maintenance has been going down. Now we have started rolling out many critical services. The more and more services we roll out, the number of hours we can get for support, get to do like configuration changes, code upgrades is going down. We got to make sure we align with all our internal teams and external teams on notification before we start taking down a box for maintenance. So this kind of puts us in a spot where it takes a long time to do a code upgrades or BAU or business as usual augments. We need to do no network to support the capacity growth. And the last challenge is the environmental demands. So we do deploy these core routers in a co-location facilities that we don't own. So some of the constraints there is always space, power, and cooling. Though we have new big routers coming into the network, they're like 200 terabits of capacity routers. The power per gig is going down with the new ASICs, but because we have more ports on a single rack, the power needed per rack is going up. So some of the new routers we are looking into, they need like 50 to 60 kilowatts per rack. And the cooling is directly proportional to the power we use and the port count we turn up on the router. And also there are some space constraints in these facilities where if you turn up a big high density next-gen routers, we would have to make sure we have enough space around the rack for the proper cooling purpose. So we end up losing more space with this new deployments, with this new big routers. So that takes me to the proposal or the solution we came up with or we went with. We decided to go with a spine and leaf CLOS architecture in our core locations. This is not a new architecture. It's been there for a long time. It's been deployed and proven successful in data centers. So we are adapting that architecture for our core backbone locations. So it does address all these concerns we talked earlier. We can pick and choose different platforms based on the roles. We have flexibility to scale up as well as scale out. We can do both horizontal and vertical scaling, and we are able to seamlessly integrate this new architecture into the existing network. So we would turn the existing core router as one of the leaf into this spine and leaf architecture, so that we don't disrupt the existing traffic flows or the demands. By taking a big router and breaking them into smaller routers, we break the blast radius now. So now with one router failure, we are not impacting the traffic flows going through that site anymore. Moving this architecture allows us to change the focus from a platform towards an architecture. So before we were always looking for a bigger and bigger and bigger platforms and aligning our deployments to the platform rollouts. Now we have this architecture. Now we have more options to pick different platforms for different roles. So now we can focus on the architecture rather than the platform. We have built with N+1 redundancy. So that means we can take the routers offline to do maintenance during the daytime, during the nighttime. We don't have that maintenance window constraint anymore. We have done hitless maintenance during the daytime now. This architecture allows us to drain traffic on one spine. So for example, if you have 4 spine or 8 spines, so you take one of the spines out, drain traffic off that spine, move the traffic over on the rest of the spine nodes, and do the maintenance and bring them back up without impacting the traffic flows through the site. So our downstream customers as well as our upstream providers don't see this maintenance being done in their network. But you guys might be wondering, so spine and leaf is there forever, I mean, more than 10, 15 years, and it's proven in data center. What is new here? What we have found out is that deploying spine and leaf in a core location has its own challenges. The requirements, SLAs, support requirements, design requirements are slightly different than the data center network. For example, in a core network, we have to support IP table, full internet table. We have 1.2 million prefixes, about 800K internet prefix. Then you have internal prefixes, so we have more than 1 million prefix we need to support. And when you bring up the BGP full mesh, there are you go from 2 million paths to 20 million paths or 30 million paths. I'll go through more details about routing later in the slide, but there are constraints, there are limitations, there are issues that we have to tackle to make this architecture work in core backbone. Now, with going from a single router to 30 node or 20 node in a site, you multiply by number of sites, the number of nodes you get to support in IGP domain is going up drastically. That means we got to keep an eye out on the IGP protocol also to make sure they are good with their scale numbers. The other constraint is the ECMP paths. Before we had one path, east or west. Now with spine and leaf, we have n number of paths, n number of ECMP paths. We could have, if you have 4 spines, there are 4 ECMP paths. It could be 8 or it could be 16. So you got to make sure that the routers we pick, they can do proper ECMP traffic load sharing. And the traffic profiles are different. We don't control the traffic profiles that we support, the transit traffic. Unlike data center, you may have your own applications. You have an opportunity to change the traffic profile if you need to with your own data center app. But in a core location, we have no control about the traffic profile. So we got to make sure we pick the right platforms. We have to make sure we have the right tools to monitor the traffic load sharing among the ECMP paths. And we also need to rework the BGP design. Before it was simple, in a backbone network, you may have like a small number of routers, maybe 20, 30 routers, or maybe 40 routers. It is easy to do BGP full mesh among all core routers. Now you go from the 20 or 30 or 40 routers to hundreds of routers. So we have to rethink on the BGP design as well. And then the other constraints the other thing we were trying to solve is the convergence. So now we have high number of BGP paths, and because of the BGP design ECMP, you have to make sure the BGP convergence is within the SLA we support. So we have to work with our vendors to make sure that the features and knobs, some of the trick we used on network with the BGP to allow the better convergence to meet the SLAs. And the last one, as I was saying earlier, we got to make sure our support organization, our operational team is on board with this CLOS architecture. They have all the tools and dashboards and the toolkits to support this network. So we have to think through to make sure how we support this network, how we were supporting single node design versus a multi-class cluster in our core backbone. And one other thing I missed, in a data center, all the links are jumpers. There are like few meter jumpers. Pretty much, once you plug them in, they don't go bad unless the optic goes bad. But here in core locations, some of the links are over, kilometer for the long haul fibers. They could be like, across the country. They could be maybe 100 kilometers, 200 kilometers, even more than that, 1,000 kilometers too. So depending on where the locations are. So we got to watch out for those, the fiber failures. How does it impact the CLOS design? How does it impact the scales we support in the CLOS designs? This slide shows a quick preview of a typical core deployment we did. So we started with spine routers. We call them CS nodes. We started with 4 CS nodes, but we have an option to go beyond 4 depending on the growth. And then we have the local PEs, remote PEs over the long haul fibers, and the CRs are the leaf nodes connecting to the spines. And we also have the regional area network that supports our customers, that directly connects to our customers as a leaf node to this CS spine. And we also have 2 router reflector. I'll cover more in the BGP design, but we installed 2 router reflector servers, and we took the router reflector function off of the routers and moved them onto this x86 RR routers. So in the IGP design, the way we have our backbone network, it's on its own IGP domain. We have a separate IGP domain for backbone compared to the regional area network. So that helped us a little bit here. So we did increase the number of nodes in the backbone now with this CLOS architecture, but we are within the limit of the IGP scale numbers. But we are closely watching, because as you add more nodes, more links, your IGP database is going to grow big. And we got to make sure we don't impact the convergence by increasing the database size. So we're closely watching the IGP database numbers. We're also looking at a few options to reduce the IGP database in future if needed. There are a few ITF drafts out there on how we can do optimization to IGP ISIS, for example, in particular, to reduce the database size. So we are closely watching those drafts. So if we need to do any optimization in future, we have few options on the table to tackle. BGP design is a little bit complex than IGP. So before we had full mesh BGP design, and now we are going away. We went away from it and we did a 2-layer BGP design. We have route reflector servers in a mesh, and then all the routers in the site would be the route reflector client for the servers. This is a 2-layer design that we are rolling out with this CLOS architecture. We have to do a lot of quite a few features and enhancements to get the convergence number we were looking for. And also we had to turn up certain features to make sure the load sharing works fine. So now we have a lot of ECMP paths. We have to turn on BGP add path feature. Otherwise, the route reflector is going to pick one path out of the all possible BGP paths and send down to the downstream clients. That means we are not going to use all ECMP paths. So we have to make sure we enable a BGP add path feature on the route reflector servers, so that the route reflector clients, the PEs and CS nodes and CRs have full view of the topology, so that they can do packet flow load sharing across all the paths, all the ECMP paths. We have also rolled out a BGP pick feature. With BGP pick feature, what it does, in addition to the best path, it also pick a second backup path and install the backup path in the fib, so that if the primary path goes away, we already have a backup path in the hardware. You don't have to wait for the BGP convergence. So you swing to the backup path immediately. So we enable BGP pick to get the better convergence. And also we need to enable BGP pick multipath, because now we have ECMP. We have 4 nodes or 8 nodes, depending on number of spine nodes we have. We have a lot more paths. So we have to make sure the BGP pick installs the ECMP as a primary path. If there are 4 ECMP paths, we install 4 BGP primary paths, then a second or backup path, which is not part of this ECMP group. So we had enabled that BGP pick multipath feature for that. And we're also working with the vendors to get additional features and enhancements to optimize our convergence. So when we turn on BGP add path, the number of BGP path explodes now. Now you have a lot of ECMP paths, a lot of BGP speakers. So then the number of BGP path explodes. To reduce the path, the more BGP path you have, it takes a long time to compute and run through the algorithm and pick the right best path during failure scenarios. So it impacts the convergence numbers. So to reduce the BGP paths, we are rolling out the Anycast BGP next hop. So what it is that we would pick an IP that is configured as Anycast among all the CS nodes within the site. And that way, the RRs and the PEs and the remote CRs, local CRs and remote CRs would see one BGP path with the next up Anycast. So we were able to reduce the BGP path by using Anycast BGP next hop. But when we enable Anycast, there's one corner case where we could impact traffic. We have to make sure if there is a link flap, if there is a BGP flap, the Anycast address is not used for that path until the entire BGP table is converged. It takes good amount of time to download 1.5 million paths and run through the BGP algorithm to pick the right path. So it takes some time. During the convergence time, we don't want to send any traffic through that path. So how we address that? We are tying BGP state or the triggers to the Anycast advertisement. So if there is a link flap on CS1, we have to make sure the CS1 is not being used as an active path. We would wait for the complete convergence of BGP before we inject the Anycast into the IGP domain. So we are using Anycast advertisement with triggers and BGP state. The other option we have deployed is advertise BGP paths with the different policies. Only the local nodes need to know the full topology of the local cluster. So we are advertising the full view onto the local nodes, local clients, but the remote clusters or remote RRs or the remote clusters, they don't need to know every path inside the local class cluster. So what we're doing there, we are advertising only the best and backup path to the remote peers and advertise full view or full paths to the local clients. That way we have a better control on how many paths we advertise to the remote RRs. We are still actively working with our vendors to find other ways to reduce the BGP paths, so we can keep optimizing as we go along. Provisioning and support, automation, and operations. Automation, it's a critical component here. We got to make sure we have automation to support this class deployments. There are 4 categories. We need automation to launch devices. We need automation to roll out configuration into the devices. We need automation to do cable validations. There's a lot of cabling now. And we also need automation to do code upgrades. So we have made a lot of good progress with automation, but we still need to work through a few things as well. When it comes to operations, we realized that we probably need more than SNMP. We need to start collecting data from the routers in a different perspective, because now we are monitoring a whole cluster that could be 50 nodes inside the cluster, but we need to find a way to get data from all those routers and correlate them and show them as a single cluster. So we started looking into telemetry data streaming. We were able to successfully get data out to those routers. We are pushing those telemetry streams into a collector that goes into a database, and we are starting to use the data sets that we collect using telemetry data streams. Before the change here, before, if there is a fabric problem in a big multi-chassis or big box, we would just make a phone call to our vendors and have them to figure out the problem and fix. But with the CLOS architecture, now we get exposed to the fabric problems, and it's on us to monitor, troubleshoot, and fix all the fabric issues between the spine and leaf nodes. So it's a little bit complex than how we were operating before with a single chassis design. So a little more on the support here. We need to make sure we have all the tool sets available to our operations team to monitor this CLOS cluster. We have to make sure we group all the routers in a cluster and show them as a single unit, so that we can find the health of the cluster. And it's critical, because if the cluster is not, if we lose one of the spine, we got to make sure we notify that to our operations. That cluster is in a failure situation. We can't have one more failure in the clusters. So we got to make sure how we monitor this CLOS components, and we got to build the dashboards and tools to show the entire group of routers as a single SRLG. So we started thinking, how do we monitor this class? So we were able to come up with 5 pillars, starting from the hardware, software, routing protocols, links, and traffic. I'll go more details about each pillar in following slides. So in a hardware, if you look at any of this new ASICs coming out, there are a lot of components inside the hardware ASICs. There are resources, there are memory tables sliced for different applications. For example, TCAM, LEM, LPM, FEC. And there are port buffers we use inside the chipset, and there are QoS buffers we need to monitor. So there are a lot of hardware components we need to monitor to make sure the hardware is working fine to the level we're expected. We're expected to them to behave. So we are looking into some of the telemetry data streams to monitor these components to give us visibility to the hardware health. Likewise, the software, we are looking ways to monitor the smooth upgrades, the smooth running in the box, the signature check of the software, and also the bugs and all other software processes. Then it comes to the routing protocol. Now we have a group of spine, a bunch of leaves. We have ISIS, LLDP running on those fabric links. So we have to monitor to make sure we track all the link failures, node failures, all the protocol states. And also we need to start monitoring, we have to monitor the BGP sessions, their states, the prefixes received, advertised between the BGP session, between the BGP peers. And also start looking into the router trend to see how stable the network is. So we have to watch all those routing details, the churn and the ISIS database and BGP table, all the flaps going on. So we have to monitor them. So that gives visibility to the routing protocols. Then the links. So we have to monitor, as I said before, we didn't have to worry about the fabric links inside a box. Now with the spine and leaf, we have to monitor those fabric links, and we have to check the redundancy for those fabrics. If one of the spine goes out, we have to monitor and notify the team to make sure they get fixed. And also there are a lot of optics here now involved. We have to monitor the receive and transmit power of the optics, the health of the optics, and see any trend that we can pick up for any issues. And the last pillar is the traffic. So as I was talking about eCMP paths, now you have to make sure that the traffic is load shared among all eCMP paths properly. We got to make sure that the packets and bits coming into the cluster are being routed out of the cluster without any drops internally. We have to monitor the drops, interface drops, null zero drops, TTL drops, no route drops, QoS drops, and hardware drops. So we got to monitor all these drops to understand what's going on inside the cluster. One thing we found in the lab testing was that during the convergence, when you have multi-level BGP sessions, if there is a failure, then the BGP has to advertise the failure to the router affected servers, and they would have to pass on that failure to the remote RRs and to their local clients. That takes a little bit of time, the convergence. So during this convergence, the only way to figure out if there are any problem with the traffic is looking into the micro loops. If there is a micro loop happening inside the network, the TTL drop count would go high. So we started looking into these TTL numbers to understand the convergence and start figuring out different options to bring down the convergence number or the recovery time, so that the impact to our customers is reduced. So the TTL drop, the no route drop, the QoS drops are critical data points for us to look into the health of the CLOS. The next slide shows some of the graphs that we started building. Again, we are very early into this telemetry streaming project. The first thing we needed to do was to find out all the data points we want to collect from the routers. There are hundreds of thousands of data points that router can stream out today, but we have to pick and choose what we are interested in. We don't want to just dump everything out of the router, then figuring out too much data to process. So based on the pillar I was talking about earlier, we have identified those sensor points. We have configured those sensor points on the routers. Now we have those streamings coming out of the routers at every 30 seconds to 60 seconds. We can go down to even 10 seconds, but that's too much, I thought. So we are starting with 30 seconds in some routers for some sensor points, but other ones we are starting with 60-second intervals. So we have turned up a collector. It's an open source collector from Cisco, Big Muddy, that takes all these streams, and we are processing them, put them, populating the InfluxDB database. And I was able to create some of the graphs here that I show. You can see the ISIS adjacency within the cluster. There are 4 spines, and you can see the total ISIS count aggregated for the cluster. And you can see the traffic load sharing among all the leaf nodes. And also per leaf node view, you can see the traffic split across all 4 nodes. And then on the right side, you have the BGP routes received. We have the fabric bandwidth being monitored by LLDP data. And also, we have the QoS drops graph that shows if there is any drop going on with QoS, we would get them here instantly. So these are some sample graphs we are building, but there are a lot of work to be done here. So now we have the data in the database. Now we need to find a way to build the tools and dashboards that can send right triggers to our operations team to react for any failures. Just wanted to give you that preview here with the slides, with the graphs. So that takes us to the last slide. We have the next-gen core cluster, spine and leaf architecture deployed broadly in our Comcast backbone. It's been there serving our customers, carrying production big for a while now. We were able to upgrade code on these boxes during the daytime. We were able to manage the traffic utilization because now we don't have a single router failure impacting multiple paths anymore. The blast radius is smaller, so we were able to manage the traffic utilization properly. Some of the lessons learned: automation is the key. Need better process and tools for operations. There's a lot of cabling work to be done. So we had to make sure we have all the tool set in place to track those cables, to fix if there are any issues with the cable on day one. So we use telemetry data set for that. Again, the design is built to last longer. So one of the learning is that you get all your physical work done on day one, so you don't have to go back and change physical cabling later later in the time. So if you can get the physical work done, it's easy to deploy more leaf nodes if needed and expand the CLOS cluster to support the demands. That brings me to the last slide. I just wanted to thank you for the opportunity to share our evolution of backbone here in Comcast. I thank Augie and Tony Tauber and other folks who helped me. This is my first NANA presentation. They helped me to navigate the process and make me comfortable to present it. Thank you.
We have a few questions, and if you have any more, please put them in the Q&A channel now, and I will relay them as we get to them. So the first question is from Dan Megorian, who is asking, how could inbox and between box speeds be similar when same chip port to port is much faster?
If I understood the question, is he asking if he's asking, did we see any change in the speed of processing in different boxes? I don't believe so. Sorry, go ahead.
I think he's asking more about how you can get enough bandwidth between boxes in a multi-node deployment versus a single Dropbox type of device?
With more spines, we were able to, with more nodes, we were able to get more ports serving the service ports we call. We were able to expand the spines as we need to increase the bandwidth. We can expand the spine and grow horizontally to support the additional ports. Yes, we have to use the ports to interconnect the spine and leaf. But I think if you scale enough in vertically, you can support the service ports.
Okay. Matt Pitek is asking, you say dashboards and tools should monitor the entire group of routers in the clusters as a single SRLG, but you created an N+1 spine so that you could fail individual spines out without causing impact. If the whole cluster is in a single SLRG, when you have a spine failure, do you fail everything out or ignore it because you have N+1 redundancy internally to the cluster?
We don't actually. So if there is one spine failure, we don't drain traffic, but we do need to mark or tag that group as a different state. It's not green anymore. It has one spine failed. So we have to mark and tag it differently so that our operations team keep an eye on that cluster to bring that spine back up, and also will stop them to make any changes to the cluster to avoid any impact.
Thank you. Chris Summers is asking, what streaming telemetry are you trying? GNMI config? And do you find consistent multiple vendor support?
No. So OpenConfig we use wherever we can, but again, it doesn't give us every data points that we want to monitor. So we are dipping into the YANG models, vendor-specific YANG models. We find a little inconsistent between the vendors. But we have to pick and choose the right models from a vendor-specific perspective till we get the OpenConfig coverage for all the data points that we would need to see.
Let's see. Michael Doherty is asking, are you integrating any RPKI or prefix validation into your redesign, either on the ingress or egress?
So there's no change in RPK deployments approach. We are still keeping how we have been deploying RPKI and the edge. So there's no change with this deployment and how we've been handling RPKI deployments.
Okay, Shraddha Hegde is asking, what is the impact of bringing CLOS in core network on traffic engineering paths? Do you have TE deployed in the core, and any thoughts about placing TE paths in the CLOS?
We don't have TE support yet, but it's something we're actively looking into. This part of the network, it's just doing pure IP routing. Now we have the topology set. We are looking to see how we could use SR to solve some of the TE requirements that would come up in future.
Let's see. Brian Holloway is asking, you mentioned keeping an eye on your L2 ISIS database. Are you considering L1, L2, L1, or did you have something else in mind?
It's one of the options on the table that we're looking into. So if needed, we can break it into big L2 domain into L1 and L2 and manage the database that way. It's one of the options we are considering.
Okay, and we're almost out of time, but we have time for a couple more questions. So I'll get as many as I can here. Let's see. Would you please give more details on how you are monitoring QoS drop?
So one of the vendor blocks that we have deployed, there is a data point sensor, telemetry sensor data point sensor path available to us. So we are watching all the queue drops for all the queues, all the QoS queues we have in our network. By looking at those queue drops, we have an idea what's going on. Is it the queue drop related to a convergence, or is it something else going on in the network? So we are using that data point to monitor the queues.
Okay, Roland Dobbins asks, can you talk about the design and scale of your telemetry export collection network infrastructure for all the various forms of telemetry you're doing?
It's still really early, so we are learning right now. So we are streaming about 100 to 200 routers now, about 100 plus routers sending telemetry streams to a collector. All data points are streamed out at every 30 seconds. Some data points are 30 seconds, other data points are 60 seconds. So it is a lot of data. We are keeping like 7 days from our 5 to 7 days retention. So we do drop those data points after 7 days after we process them. But it's an early stage. We are still trying to understand the scale we need to deploy to support the telemetry to retain the data longer period.
Okay, and one last question from Blake Willis. Any more details on how you anycast BGP next hops in the core, please?
Sure. So if you have like 8 paths to an eBGP session or an external network, you would learn like all the BGP prefixes from that BGP peer, and you would have 8 different next stop. With the add path enable, now you're going to send 8 paths times number of prefixes you would get from the customer, from that external AS. So this multiplies, if you have more and more spines, more and more external peers, more prefixes coming in, the number of BGP path explodes. So what we are doing instead, we are using an Anycast, virtual Anycast IP per cluster, and we are setting that Anycast as a next stop, BGP next stop. So now we go from 8 paths to 1 path with the Anycast BGP next stop. So that way we were able to control the BGP paths in our core network with this CLOS deployments.
All right, thank you. We're out of time for questions, but if any of you have anything else, please continue in the chat or contact him offline.